Okay, welcome to the second example. In the chapter of stress, the question reads, the rods A, B, and CD are steel with tensile failure stress of 510 megapascals. Using a factor of safety of 1.75 for tension, determine their smallest diameter so that they can support the load given. The beam is assumed to be pin connected at points A and C. Okay, so we are going to start with givens, and you are given a lot of stuff in this question. Just to get it out of the way, we have pins at points A and C. Now we can get on to the fun stuff, where we talk about rods A, B, and C, D, which are the main focus of this problem. We want to find their diameter, and since I already said it, let's just scurry off to unknowns and then come back to givens. So unknowns, I want to find unknowns. I want to find the diameter of AB and the diameter of CD. Let's go back to givens. Okay, we're given that for these two rods, they have a maximum fail, or the stress that they fail at. So the maximum stress that they can handle, or sigma max or sigma fail, is equal to 510 megapascals, right? We're also given that the factor of safety of these lovely rods is 1.75. What is the factor of safety, and how does it relate to the maximum stress of these two rods? Well, the definition of the factor of safety is the ratio of the maximum stress a material can handle over the allowable stress, or the stress that is going to be normally subjected, basically the stress that a material will normally encounter. Why does it matter? Should this number be up or down? Well, it's a ratio, but generally you don't want, as this number increases, it gets more safe, but other things like cost and weight and you have to test it more to see if it actually, there's a lot of other factors. You can't just make everything as safe as possible, because unless it's for example, I won't give exact numbers, but for example, if you have an elevator, right? You have your good brother right here, he's in the elevator, and you have the end of elevator tension cable, right? This is an example of where you need a high factor of safety. Why? Because I'll just give random values. There's no way the actual value. Let's say the allowable stress, or the normal stress that's basically this elevator handles on a daily basis, is 100 megapascals. Again, this is not realistic numbers, but just as an example. I want to design this so that regardless if something happens, I want the maximum stress of these tension cables. I don't want it to fail at 100. I want it to fail at 300, even though there's probably there's no chance that it'll even get to 300. It won't reach this level of stress. But I want to design it in a way, and I want to make this material in a way that it'll have a factor of safety. In this case, if we use the formula, it'll work out to 3. So you have a factor of safety of 3, and that's a pretty high factor of safety. Why do I want this? Because even though it'll cost me more, it might be a bit more expensive, I have to test it more. If this thing fails, especially nowadays, buildings are just getting higher, that is going to be catastrophic. That is going to be a big problem, because if this thing fails all of a sudden, you don't want that to happen. So that is one of the reasons. So the stakes are higher, basically. Higher factors of safety also occur in things you see the space applications, like surgical robots, where very tight precision is needed, and stuff like that. Lower factors of safety, an example, maybe the bumper of your car, because it absorbs. It's supposed to deform upon impact to protect you and protect the more important components of the car. Your phone casing, for example, it'll break more easily. It may be designed, for example, 100 megapascals of stress, but the maximum it can withstand is maybe 120, right? That's a pretty low factor of safety. If you just do it, if I do it quickly, 120 divided by 100, 1.2, for example. That's a factor of safety of 1.2. Why? Because they want to keep it lightweight, they want to keep it cost efficient. It's designed to get dropped or something, but not to get smashed on the ground. And also if it breaks, you get to buy another one. So it all falls into, there's a lot of separate other categories that you look at. So you don't want to make everything as safe as possible. But that's the conceptual part the factor of safety. Hopefully that was understood. Okay, that's the factor of safety. Do I know sigma max? Yeah, I do. I know factor of safety. I probably will need it in this question. I want to know what sigma allowable is. And I know the sigma allowable is, what is it? It is the force over the area. And since we have, it's asking us to find diameters, the area is going to be, again, pi over 4 d squared, right? D squared. Perfect. So pi over 4 d squared. Perfect. The game plan. So basically, we want to find DAB and DCD. I basically can isolate for diameter. I can isolate for diameter in this equation, and then I can find sigma allowable using this. Perfect stuff. But first, I have to find the force, right? I have to find this force CD, which is causing the tensile loading, or it might go down, I'm not sure. And then I also have to find this force AB, right? And I will do that via free body diagram. The beam will look like this. You have points C right here. You have points A over here. If you draw the dimensions, this is 3 meters, this is 3 meters, 2 meters, 2 meters. You have force AB, force CD, 5 kilonewtons, 6 kilonewtons, and 4 kilonewtons. How am I going to find FCD and FAB? We did a lot of review statics, so this should be very simple, because all we need to do is take a moment about FCD. This goes away. I have to take account to this. I have to take into account these forces, and my only unknown is FAB. I can find FAB, right? If I take a moment about point C, and then I'll have FAB, and then I just take the sum of forces in the y direction. Since I have all 4 of these at that point, I can find FCD. Should I do it? Why not? Okay. Counterclockwise is positive. If I take a moment, in my notes I did about point A, so I'll do point A. Same thing. If I take a moment about point A, this one goes away, and then you take into account this force instead, and then you'll find this one, and then you take sum of forces in the y direction, and then you find this one. But same way, either way. So if you take a moment about point A, you're going to have clockwise, 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 negative, counterclockwise, positive. Negative 4 kilonewtons times 2 meters minus 6 kilonewtons times 4 meters minus 5 kilonewtons times 7 meters plus FCD times 10 meters. You're going to get that FCD is equal to 6.7 kilonewtons, and from that you're going to take a sum of forces in the y direction. You're going to get that FAB is equal to 8.3 kilonewtons. Perfect stuff. Now I'm going to find the diameters. So find diameters. Find diameters. 4. And then I want diameters of AB and CD. Perfect. A way I like to do these type of equation problems is I start with my unknown, so my final answer. I want to find this, right? And then I start webbing out. So I say that, okay, I know that I can use this formula, right? Sigma allowable for AB. Let's start with AB. So I know sigma allowable is equal to the force AB, right? Force AB divided by pi over 4 DAB squared, right? I can isolate this. It makes stuff messy if I like take the square root when I isolate, so I'll just keep it as DAB and then take the square root at the end. So DAB squared is equal to FAB divided by sigma allowable times pi over 4. Right? Do I know FAB? Yes, I do. I just found it. Do I know pi over 4? You betcha. Do I know sigma allowable? No, but I can find it from this formula up here. So what I'm going to do is I'm going to do another branch. I'm going to say, okay, sigma allowable is equal to sigma max over the factor of safety. I think I got that right? Yep. And I'm going to sub it back into this formula. So now I can come back from here. I can say that DAB with my final formula is equal to the square root of FAB over sigma max over the factor of safety times pi over 4. And then that should give me my answer. And then also for CD, it's the exact same thing. So this will also give you your answer for CD, dCD, by the same derivation. But instead, you're going to do 4CD over sigma max divided by a factor of safety times pi over 4. One quick check. Yes, perfect. So for CD, you're going to get your diameter. You're going to plug in the numbers. Again, you have FCD. You found it over here. You have sigma max. The question gives it to you. Factor of safety, you have it. The question gives it to you. Pi over 4 is a number. You're going to get that this diameter is equal to 5.41 millimeters. You're going to get that this diameter is equal to 6.02 millimeters. 1 point. Please do not forget to convert kilonewtons when you plug it in here, because we explained it before, but where's the formula? This formula. Sigma allowable is in megapascals. Megapascals is equal to newtons per millimeter squared, right? If you plug this in like this, you're going to have kilonewtons, and then your diameter is going to be millimeters squared. So that's why you just need to convert it to newtons, and the only way, an easy way to do that is just multiply this number by 10 to the power of 3. Perfect. That is your diameter of rod AB, and that is your diameter of rod CD.